Okay, I want to talk about how we can use the separation of variables routine for a particular model called the logistic equation and to develop what's called a logistic function. And this is a correction to typical exponential growth models, which predict unbounded populations in time. And we know that's unrealistic. Populations should converge to some sort of be limited by some sort of carrying capacity and therefore converge to some sort of horizontal asymptote. And so I want to just review the separation of variables routine. Then I also want to derive the logistic equation. As we're going to see, it's a correction to our exponential growth and decay models. And just to show you what a curve may look like if you have a logistic function as well. This particular logistic equation is going to be a first order differential equation, and it's also solvable using the separation of variables routine. And what's also really pretty about it is once we've solved it one time, we don't need to solve it again, and we're going to derive the logistic function, and we'll be able to utilize that for different situations, similar to Newton's law of cooling. Once you've gone through the modeling process of Newton's law of cooling, then I derived the function and I could use that in different situations. Without further ado, I want to review a little bit about our separation of variables routine. We're looking at first order differential equations. Remember, it's first order because what you see here is the first derivative, and that's the highest order derivative that we see. So it's a differential equation because it has a derivative in it. It's a first order differential equation because the highest order is a first order. Okay, this is separable because I can subtract the f of x to the right hand side, and I could then integrate both sides by separating the variables. Sometimes I may write dy dx is equal to a function of x times a function of y, and that's the case also of a separable equation. And here's another one as well. So here's an example. Suppose I have e to the x plus y prime equals a 0. I can subtract over that e to the x. Oops, I'll make a little tiny change right here. I meant to have a minus e to the x there. So if I add the e to the x over to the right-hand side, I could then integrate both sides, and then by the chain rule, dy dx is equal to dy, and we just get 1/2 y squared equal e to the x plus some constant. And if I multiply both sides by 2, I would have a 2e to the x plus some arbitrary constant. I'm just absorbing that 2. It's a constant trick. And so I have an implicit equation for y. This function, or say this equation, satisfies this differential equation. Okay. Here's another example, a little more complicated than analysis, but I have a function times y prime, and I have some other function. Can I get all the y terms to one side? Can I get all the x terms to another side? This is the initial condition that's going to be used to determine the arbitrary constant. We didn't have an initial condition here, so we just got the general solution. And I'll write that down. This is the general solution. In this case, we're not going to get just a general solution. We're going to get the particular solution. So we're going to divide through by 1 plus y squared, divide through by 1 plus x squared, and we end up with this differential equation. Now, this really is dy dx, and I'm using my differential form here. You can think of, I'm treating the dy dx like a fraction, and I multiply both sides by dx to write it in this way. I didn't do that up here. I just want to show you a difference of two different ways of looking how the integration routine would happen or occur. So now you integrate both sides. This is a nice u substitution. If I let u equal 1 plus y squared, then I would get 1 over u here, and I can integrate up, and I get the 1/2 the natural log of u, and I substitute back in, I get 1 plus y squared. Same integrals on the right-hand side, plus some arbitrary constant. I'm using c twiddle. Let's multiply both sides by 2 to get c twiddle twiddle. Okay. Let's exponentiate both sides, so you get a 1 plus y squared equals to a 1 plus x squared, and the constant using our exponential rules just goes in front. If I solve for y squared, we get this general solution. And now if we use the initial condition, we can evaluate this at x equal to 0, and you get √3 squared. Okay, so I have there's a mistake here. This is root 3 squared. Okay. Then I have c would then equal to root 3 squared, which is 1 plus 3, which is equal to 4. And so therefore, if I plug that in, our solution is minus 1 plus 4 times 1 plus x squared. And if we simplified, let me erase this. If we simplified, we'd have 4 and then plus 4x squared. The 4 would combine with that minus 1 to give us a 3. And I have 3 plus 4x squared. And that would be our particular solution. So y squared is equal to 3 plus 4x squared. If I subtract that over, that's the equation of a hyperbola. So this differential equation solutions graph is hyperbolic. Okay. Now let's talk about the logistic equation. Okay. It's a correction term to an exponential model. It accounts for some limiting behavior. You can think of logistic equations are used in population models, are used in also growth curves for revenue calculations, all over the place that you see this in applied mathematics. But the logistic equation you can think of, we first have exponential growth of some sort of population, but that exponential growth cannot grow unboundedly forever. And so what we see is that we are going to have some sort of saturation of that growth, because this could be interspecies competition for resources, as we have in a biological system. And that's going to retard the growth of that population. And so we see it saturating and should approach some sort of limiting capacity. We often call that the carrying capacity of the ecosystem. Okay. And so what you normally have in an exponential growth model here would be as if alpha is greater than 0. You have the change in my population is proportional to my population size, and the alpha is our growth rate. But we realize that's not realistic. It must be limited by some sort of carrying capacity. So let me make this darker. So I'm going to multiply by a correction term, 1 minus p over k. K is the carrying capacity. If you notice, if p is greater than k, if p was greater than k, then this, what I have in black, would be negative, causing the overall sign of the derivative to be negative, will cause the population p to start to decrease. If p was less than k, then this coefficient is positive, meaning the dp dt would be increasing. But notice as you get close to k, this coefficient gets smaller and smaller, it gets closer to 0. It slows down the growth. Okay, this is our correction term that we have. Okay, and what's beautiful, it is also a separable differential equation. We can get all the t's to one side and all the p's to this side. So I'm going to multiply both sides by k. And I have k dp dt equals alpha p k minus p. And then we could divide both sides by p k minus p, and we're just left off with alpha on the right-hand side. So this is all the t terms per se. This is alpha times 1. And then we can integrate. And this rational function, you can use partial fractions to separate these two. If you're using Mathematica, there's even a built-in routine called reduce. And so you can separate them. Now these integrals are doable. I've already integrated the right-hand side, alpha t plus some c twiddle. So we integrate this to get natural log of p and then a minus natural log of k minus p. You can combine the natural logs, and then we can exponentiate both sides. And what's beautiful, I can drop the absolute value sign because that's always going to be a positive quantity. And if I solve for p, you end up with this in the box, and we call this the logistic function. This is the logistic function. Alpha is still the growth rate, k is the limiting capacity, and notice when t goes to infinity, then the denominator would approach 1, and so the overall this function would approach k. So what I put over in Desmos here is, let me get over there, is that particular function. I'm using x as the independent variable here, but k is our carrying capacity, c is some constant of integration, and alpha is our growth rate. And so what I have is a picture of p of t over time, And you can see I have exponential growth here. And then there's some inflection point that happens because this is the location where the correction term is going to start dominating the behavior, and it saturates the growth, and then it starts to approach that horizontal asymptote. This is a logistic curve, sometimes even called the S curve. If I increase the carrying capacity, it just stretches out that function. It's a vertical transformation. You remember that from pre-calculus. This is just influencing, it's stretching it vertically. Okay. Increasing the decay rate just makes us go to the horizontal asymptote faster because you just increase how fast this goes to zero. Okay. So you can think of in the COVID-19 outbreak, that alpha is very, very, very large, causing exponential growth to happen incredibly fast to get towards the limiting capacity. And you can think of what a lot of the social distancing practices that are being deployed by many countries across the globe during the pandemic is trying to get one that when it gets to a limiting value, it's below the total amount available for the healthcare system. But you can play around with these individual terms and to see what happens. But that's a logistic function. Exponential growth at first, followed by saturation towards a limiting capacity. That's what a logistic function is. So it's cool. It's if I have a logistic model, dB dt equal 3p, 1 minus p over 400, we can just, right from here, we can translate to what alpha is and what the carrying capacity is. Alpha, the growth rate is 3. There's the exponential growth. This is going to look like e to the 3t, but then it's going to start being saturated, and it's going to start approaching 400. So we can automatically know what the graph is going to look like in this particular problem. It's going to start off at some non-zero value and go up to 400. And we know this shape right here, that part right there looks like e to the 3t. Saturation towards 400. We know the solution is 400 over 1 plus c e to the minus 3t. There's the general solution. You give me what the initial population is at t equal to 0. I can plug that into here and be able to determine a particular solution for that c. So hopefully that gets you started with your understanding of the logistic equation, how it's a good application of the separation of variables routine. It's again a first order differential equation that we can solve, and it has a good applications in population dynamics and other particular ones where we're modeling some growth. And I'll stop the video and I hope that was enjoyable for you.